Hello lovelies, and thank you for joining us once again. In today's chemistry class, I'm going to show you how to derive the relationship between Kc and Kp. Now you might wonder, what is Kc and what is Kp? Well, in the context of chemical equilibrium, Kp simply refers to the equilibrium constant in terms of partial pressures, while Kc refers to the equilibrium constant in terms of concentration. Well, Kp is not equal to Kc, but they have a relationship, right? Sometimes they're not equal. The only time Kc and Kp are equal is when the change in moles equals 0. And I'm going to show you today how to derive this very relationship. So the relationship between Kp and Kc is given by the expression Kp equals Kc times ROT raised to the power delta N. Well, this is our Kp, here is our Kc. The R simply refers to the ideal gas constant, which is 0.08206, while the T refers to temperature in Kelvin, and delta N, this is delta N, not triangle N. Delta N refers to the change in moles, right? Now, let's go ahead and see how we can derive this relationship. Before we begin, there are 4 things you must know. The first one is how to manipulate the ideal gas equation, or how to make P, which is pressure, the subject of the formula. That's the first one. The second one you need to know is how to write the Kp expression. If you know how to write a Kp expression, it's going to be easy for you. Number 3 is how to write the Kc expression. If you know how to write a Kc expression, it's also going to be easy for you. And lastly, you must know the basic laws of exponents, because with that, we're going to derive this very expression. It's going to be easy for us to simplify and to work with. Now, let's begin. Let's assume we have reactant A plus reactant B. These are 2 reactants on the left. And so they react to give us products, and those products are C and D. Next up, we're going to attach their stoichiometric coefficients. Now, what are stoichiometric coefficients? For example, let's say you have ammonia, NH3, right? There is an invisible one attached to the NH3, right? Now we can say we have 1 mole of ammonia. What if I write it as a 2? This means we now have 2 moles of ammonia, and this 2 is the stoichiometric coefficient of ammonia. Now we're going to add stoichiometric coefficients. This is a small letter A, we have a B, we have our little c, and our little d. These are called stoichiometric coefficients. Next up, we're going to write our Kp expression for this reaction, right? So this is a reaction at equilibrium, and we're going to write our Kp expression for it. How do you write Kp expressions? Well, it's always products over reactants, right? It's products over reactants, but it's in terms of partial pressures. It's product over reactants. Now let's write our Kp expression for this. For this first one, we have partial pressure of C, right? If you write it this way, you raise it to the power of its stoichiometric coefficient. The next one, we have partial pressure of D raised to the power D over. Now let's pick the reactants. We have partial pressure of A raised to the power A. And lastly, we have partial pressure of B raised to the power B. Now we have our Kp expression. At this point, what are we supposed to do? This simply means partial pressure of C, partial pressure of D, partial pressure of A, and partial pressure of B. Remember, it always has to be products over reactants, okay? Product over reactant, and on the numerator we have our product, and below we have our reactants. Now, the next thing that we're going to do is to derive an expression for pressure from the ideal gas equation. So we assume that these are gases, right? These are gases. Now let's go to the ideal gas equation. Here we have that PV is equal to nRT. All right, PV is equal to nRT. At this point, we're going to make P the subject of the formula by dividing both sides by V. If we divide both sides by V, the the V cancels out with the V. We're left with the P equals nRT over V. Now, remember that the numerator are actually multiplying themselves. So I'm going to separate this. I'm going to bring it this way. We have P equals N over V times RT. All right, so P equals N over V times RT. We've not changed anything. If you see this as over 1, we've not changed anything yet. This N times RT will give you an RT, and the V times 1 would also give you a V. Hence, we've not changed anything yet. Now, what is N over V? N over V simply refers to concentration, right? So it's moles over volume. Moles over volume will give you the concentration. Now we're going to replace the N over V with concentration because N over V is simply molarity or concentration. Hence, we shall have P is equal to CRT. This is it. Remember, I told you when we were starting the lesson that you need to know how to use the ideal gas equation because it's going to help you to solve for pressure or to derive an expression for pressure. Next up, we're now going to substitute the CRT for pressure. What's going to happen right now is that wherever we see pressure, we replace it with CRT. Okay? So let's go ahead and do that. Let me continue from here. So right here, we have that our Kp equals, I'm going to open a very big bracket here. Now, remember that the C refers to concentration, and we use a square bracket for concentration. For the concentration of C, I'm going to use a square bracket. This means concentration, and we multiply it by RT. Okay, we have RT. I'm going to close this bracket and raise it to power of C. Okay, and for the next one, we have the partial pressure of D. I'm also going to open another big bracket with a square bracket inside that denotes concentration because it says that concentration multiplied by RT will give us the pressure. So these are actually individual partial pressures of these gases. There are about 4 gases here. We assume that A, B, C, and D are all gases. So we're going to use this square bracket for concentration. Now the next one is our D. We say the concentration of D. Remember, this C here refers to concentration, and we use square brackets to denote concentration. Now, the next thing is to multiply it by ROT again, and we raise it now to the power of D. This is over. What's at the denominator? We have the partial pressure of A. We also do the same thing for A, where we say the concentration of A multiplied by the ROT raised to the power of A. And lastly, we do for the last one, which is B. We say the concentration of B multiplied by ROT raised to the power of B. At this point, we are going to separate them, right? We're going to separate them so that we can have the Kc expression on its own and we have the ROTs on its own so that we can be able to simplify the expression. All right, and this is where the concept of exponents comes into play. This is where it comes into play. Let's see how we can work this out. Okay, remember that this C, okay, or this exponent C affects everything inside. For the first one, the D affects everything inside. The A also affects everything inside, while the B also does the same. Now we're going to separate them. We shall pick the concentration and multiply them. We multiply them separately and raise them to the power of C. Now we also separate the RTs and also raise them to their respective powers. Let me show you what I mean here. Our Kp will now be equal to, so here we have the concentration of C, okay, raised to the power C multiplied by RT. Remember, we use these square brackets to denote concentration. Okay, now it's going to be raised to the power RT, to the power C. And next up, we have the next one. This is our D. Okay, our D raised to the power of D. Remember that they are multiplying. And the RT will come after it, raised to the power of D. This is over the denominator. Let's bring out the concentration. Here we have the concentration of A multiplied by the RT. We raise them both to the power of A. Remember that their powers affect them because they're multiplying. If you have something like A, B, C raised to the power A, this A will be distributed across everything inside. That is also how it works here. And that was what I talked about, understanding the basic laws of exponents. Next up, let's do for the concentration of B. Here we have concentration of B raised to the power of B multiplied by RT raised to the power of B. Next up, what do we do? Remember, we're not going to try to combine the concentrations and separate the ROTs. From here, we can be able to derive the Kc expression. I'm going to show you what I mean as we progress in the course of this video. Let me write this as we have our Kp is equal to, I'll pick the concentrations and bring them together, while the ROTs will be different or will be placed differently. Therefore, we have the concentration of C raised to power C multiplied by the next one, which is the concentration of D raised to the power of D, right? Now, let's pick the ROTs. I would say times, we have the ROT, the first ROT, which is this one, raised to the power of C. And the next one is ROT raised to the power of D. We have just rearranged this. Remember that multiplication is commutative in the sense that it does not matter the order. All of these are the numerator are multiplying themselves, so it doesn't really matter the order. You still get the same answer. For example, 2 times 1 is equal to 2. 1 times 2 will also give you a 2, which means that multiplication is commutative and the order does not really matter. Now let's divide it by the denominator. I'm going to pick the concentrations just like I did for the first one. And here we have our A raised to the power of A. We pick the B. We have our B raised to the power of B. Now let's pick the ROTs. This is multiplying. Let me put this the multiplication sign here. We have our ROT. Our ROT is raised to the power of A, the first one, and the next one is raised to the power of B. Okay. What's the next thing to do right now? We need to understand that according to the laws of exponents, if you have two like bases that are multiplying each other, it is right to add their powers. For example, if you have A times A times A. These are the bases. A are the bases and they are the same. So all you have to do is to say A1 plus 1 plus 1. This gives you 1 plus 1 is 3. So this is equal to A cubed. We're also going to employ the same method here in the sense that the ROTs are multiplying and they also have the same basis, right? So we can add their respective powers. How do we do that? Let me write this up here. Therefore, we have our Kp is equal to, let me also write this case expression. We have the concentration of C raised to the power of C multiplied by the concentration of D raised to the power of D. And remember, this is ROT, and they're multiplying. So we simply say ROT C plus D. They're multiplying, so we simply add their powers. And at the denominator, we have A raised to power A, the concentration of A, okay, raised to power A, multiplied by the concentration of B, raised to power B. And remember, at the denominator here, ROT, the two ROTs are multiplying, so we also apply the laws of exponents and add their powers. Therefore, we have RT, and what are the exponents? A plus B, A plus B. Okay. Now at this point, what's the next thing to do? This is simply our equilibrium constant expression. If you are familiar with this concept, how do we write the equilibrium constant expression for A plus B reacts together and gives us C and D? This is a reversible reaction, just as I've denoted it using two arrows showing one going forward and the other going backwards. This is simply the equilibrium constant, and if you want to write the Kc expression, it's the ratio of the product over the reactant, each raised to the power of their stoichiometric coefficient. Let me show you what I mean. If you have, these are the reactants, and here you have the products, it's always product over reactant, right? So it's concentration of C, which is the product raised to its stoichiometric coefficient multiplied by the concentration of D raised to its stoichiometric coefficient. And now let's go to the reactant. We have the concentration of A, okay, raised to the power of A. And lastly, the concentration of B raised to the power of B. Well, we now see that there is a similarity between this and this. This right here, the C, D, A, and B are the same with this, right? This one from this part here is equal to this. They are both the same. Now, what we're going to do now is to replace this entire expression by Kc. Okay, we replace everything here with Kc. Let's quickly do that. Our Kp would now be equal to Kc. Remember that this is the Kc expression for this very reaction, which is at equilibrium. Now, this is also multiplying with the two ROTs, so we can say times ROT raised to power C plus D over ROT raised to power A plus B. Okay, we can say this is Kc over 1, so we've not changed anything yet. We only changed this expression, which is equal to Kc itself. Let's simplify it over here. Okay, here we have Kp equals Kc. Remember, we found our equilibrium constant expression in terms of concentration, and we replaced it with Kc. Now, the next thing that we're going to do is also to remember or to recall that if you have like bases, like for example, A cubed over A squared, based on the laws of exponents, if you have two like bases that are subtracting, you simply subtract, two like bases that are dividing, you simply subtract their powers, right? A and A are like bases, just like we have RT and RT are like bases. So if you have like bases that are dividing, you simply subtract their powers. That's according to the laws of exponents. Now, for example, let's say I don't want to do that. I divide, I remove 2 from here and 2 from here. We're left with an A. Now, it's also the same here. A, 3 minus 2 is just a 1. And any number raised to the power 1 is the same number, just like that. We're also going to employ the same method here by subtracting the powers. This is now going to be Kc times RT, okay? And we have C plus D minus, I'm going to put this in bracket, minus A plus B. The C plus D comes from the numerator, while the A plus B comes from the denominator. They are like bases, so we can subtract the powers. Now, what is C plus D and what is A plus B? Remember that this small letter A, B, C, and D are simply referring to the moles of the product, of the product and a reactant, right? Now, this is our first reactant, and its mole is A. The second reactant, the mole is B. Just like you have NH3, right? Now, if you have 2 moles of NH3, this stoichiometric coefficient here simply means that NH3 has 2 moles. That's the meaning. Now, if we look at this, C plus D minus A plus B simply refers to change, right? This can be seen as a final. This is the final, the C plus D is the final, while the A plus B is an issue. As we have here, we have that the C plus D are the product. So initially you have to start with your reactant and you end up with the product, right? So the A plus B is the initial, while the C plus D is the final. For example, let's say in physics you want to calculate displacement. Displacement is given by change in x, right? Change in x, which is x2 minus x1, which is final minus initial. We're also going to employ the same method here. So we shall say this is now change in moles, okay? Because these small letters here are talking about or are referring to the moles of the reactants and products. Now we say change in moles is equal to C plus D minus A plus B. Or we can also write this as change in moles. This is equal to product, okay, minus reactant, right? So the product is the final while the reactant is the initial. Now, what we're going to do right now is that we're going to replace the C plus D minus A plus B with change in moles or with delta N. Let me do that here. If we do this replacement, what do we get? We have Kp is equal to Kc. I'm going to put this in brackets, RT multiplied by, raised to the power, delta N. Hence, this is the formula or the relationship just as we wrote initially between Kp and Kc. This is how to derive this very relationship. And the only time Kc and Kp are equal is when the change in moles equals 0. If it's equal to 0, you will now have Kp equals Kc multiplied by RT. If the change in moles equals 0, you shall raise this one to 0, and any number raised to the power 0 is 1 apart from 0. Hence, Kp will be equal to Kc. Because if you raise this to the power 0, this RT becomes a 1. Kc times 1 is Kc. Then Kp and Kc will now be equal. So this is how to derive this very expression between Kp and Kc. In our next video, I'll show you how to use this relationship to solve for either Kp or Kc when one of them is given. I believe you enjoyed this interesting video on how to derive the relationship between KP and KC, I would encourage you to subscribe to this channel and turn on the notification bell so that you will not miss other interesting videos like this. Thank you and see you some other time.